Hi, my name is Thomas Frekhaug, and as you know, I am a PhD student in aerospace, and I am working on guidance and control in non-conventional scenarios. I'm recording this because I'm currently on traveling and on my way to a research day, so I'm sorry for not being there in person. My supervisors are also Manuel Sanjojo and Professor Manuel Soler. So, small body operations or operations around small celestial bodies. So, exploration of small bodies in the solar system is on the rise, and it's expected that in the next tens of years there are going to be many more missions to explore both small planets and moons, but also asteroids and comets. However, these types of operations are very challenging because of all the environment they are going into are very uncertain. So, for example, we have the ESA's Comet Interceptor, which is being in development right now, which is currently targeting a comet or asteroid that they don't even know when anything about before it launches. So with this, of course, we have the uncertain environment, but also these types of bodies are often far away and there are substantial time delays when communicating with the spacecraft. Finally, the spacecraft may also have failure mode, so things that can go wrong in the spacecraft, and as such, the spacecraft should be robust towards this. In general, the current experience for operations around small bodies is in its infancy, and there is lots of room for improvements. As an example, we have two recent successful missions, the OSIRIS-REx by NASA and the JAXA's Hayabusa 2 mission, which both were successful, but also are relatively rudimentary in the way they perform these operations. So for autonomy in space, which is what I am interested in, we need more of it. And what is the advantage of a higher degree of autonomy is that, of course, we get higher increased turnaround time of missions and simplified missions designs because of if an autonomous system must be able to deal with any uncertainties that are in present and are in general more flexible to more larger area of systems. This requires the development of robust guidance and control laws, and it requires for the spacecraft to become independent from the ground control. And there are different methods of doing it, so I will come back to it later, but most promising is the Convex Optimisation for guidance and machine learning reinforcement or similar machine learning and reinforcement learning algorithms. But of course, this is more questionable to put into high risk missions. So probably the way forward is convex optimization. And as an overview here, you can see in the general in guidance, navigation, and control in aerospace, you have two branches, explicit and implicit guidance. And you can see here on my left side here, separate guidance and control. This is what has been the normal thing to do up until now, where you design a control algorithm and then you control a guidance algorithm separately, and then you hope that they work fine together. However, now when you want increased autonomy, it is much better to incorporate these designs and have a so-called integrated guidance and control system. And one promising approach for this is something called computational guidance and control. Computational guidance control is basically dependent on solving an optimization problem in real time on board the spacecraft. And this optimization problem can have many different forms, such as convex optimization, it can be non-convex, or it can even be solved by machine learning or reinforcement learning algorithms or ways to solve a dynamic programming program. But in general, for my research, I have been focusing on quadratic programs, which is here on the bottom left, where I have been focusing because of its simplicity in computational demands. So, what is a convex problem? A convexity problem is basically any optimization problem that has a global unique solution and that all the constraints are convex. And then you can, of course, go further down the rabbit hole and find second order programming and also quadratic program, where each step downwards you go, the faster and simpler the optimization program becomes, but of course, usually at the cost of accuracy. So you have to have a linear model, for example, in a quadratic program, which is of course then less accurate than a nonlinear full description of the scenario. So another advantage of a quadratic problem, which the way you can see is outlined here, is of course that there exist very many fast solvers already off the shelf that you can use to solve these optimization problems in the matter of milliseconds. So that's an advantage. However, they are using computational guidance and control with these kind of quadratic programs. It is challenging because the robustness of these solutions are not given. You have to specifically design them into it. So the one specific computational guidance and control method is something called model predictive control. And model predictive control, I'm going to go more into that exact what it is details later. But imagine you can see the graph here above me, where you have your blue line, which is the path that you have taken on previous trajectories. And then at the current timestamp, you are going to predict into the future. And then, of course, you have uncertainties. So the future can develop in many different branches, as you can see here by the gray, blue, and red branches, where, for example, the red branches are the one that has like the extreme cases of the evolution of the uncertainties. And then, of course, all of the other ones are just different scenarios of different uncertainty evolution. And based upon this, you can solve this optimization program. You can solve it in different ways. And depending on what your goal is, you can, for example, do stochastic optimization, where you try to minimize the variance of these of the evolution of the trajectories. You can minimize one of the scenario. You can minimize the moments, or we can use something that's called deterministic, where instead of looking at all of them together, we either choose minimax, which is just taking the worst case scenarios, or what I will be working is the tube-based methods. The tube-based methods is basically a compromise between the stochastic and minimax, where you try to take all of them and then you leverage the advantage of the MPC that you continuously compute an optimization to write a new solution. And of course, this exists in various versions. So I'm not going to go too much into the details, but the baseline of it is that we have a true system here on the left, which has some uncertainty in it. And then we want this true system to follow a virtual linear system on the right there, which you can take subtract this from each other, which gives you the aerodynamics you can see here in the bottom. And of course, for the true system to follow the virtual system, the aerodynamics needs to be stable. And but the uncertainty is propagated into it, and as you can see by the delta here, there is uncertainty in the aerodynamics, which means that the best we can hope for is to the aerodynamics to converge to a minimum set, which is defined by the uncertainty. This minimum set is called the minimum robust positively invariant set. So we can compute both of these feedback gain that we saw in the previous set and the minimum in the robust positively invariant set from the equations that we see here, which is one of the proposals that we have done. This is just a simple linear matrix inequality, and then you solve it sequentially, and then you can see the bottom here how to select the feedback gain K. So advantageously, this optimization problem also gives us an approximation of the robust or an ellipsoidal robust positively invariant set. From this ellipsoidal robust positively invariant set, we are able to create a hyperbox of a bounding box. And this one is what we are going to use in our model predictive controller, where we create a bounding box around this, and then we use a linear optimization problem, you can see here, to scale it such that the resulting set is actually robust. This you can see here. So you can see here the minimum set is the black one in the middle there, and then you have the ellipsoidal set as generated by the linear matrix inequality we have shown. And then you have the bounding box in the red there on the outside, which is the approximation of the ellipsoid. And then we can use the linear equations that we have seen to scale it properly, such that it is guaranteed that this set is an invariant set, which is what we need for this for the MPC. So with all of this, it is possible to construct an MPC. And this you can see the MPC model predictive control in its wholeness on the left side here, where you have some constraints. The first one is just a model of the system. The second and third one is just the inner constraints on your input and your state. The fourth one is just more or less your initial conditions of the state. And then the fifth and sixth are just additional constraints that we have to ensure that our uncertainties are coherent with our MPC when we propagate, and that the state is selected properly so that it does not go outside. A visualization of all of these sets is seen here on the right, but I'm not going to go too much into that. So for the MPC then, we basically solve this optimization problem here at every discrete time step. And then we take the first input, U0, and then apply it with the feedback law that we've seen previously. Then you get the MPC. So moving on more to the actual circumnavigation and descent. So for circumnavigating an asteroid, you of course need to go around something while keeping outside the centroid ellipsoid. And of course, this is a non-convex, keep a non-convex constraint. So we need to convexify it. The way we convexify it is that since we solve an optimization problem at each time step, we basically we have a trajectory from a previous time step where we will give you to the goal, as you can see by the illustration here. And then you just find the intersection point between this trajectory and the keep out zone. And from there, you can Taylor expansion and get a linear plane at that place, which just basically will linearize, will give you a linearized state space for that collocation point there. And this we do then at each step. You relinearize it at each time we want to solve this optimization problem to get it to be linear at all times. And then furthermore, we also need to be tightening this one, which we have shown that how to in the papers that we have. We show how to actually tighten these or constraints. So this type of constraint or convexification actually works in a robust manner as well. So what are the advantages of this, the things we are proposing? So one big advantage is that we have guaranteed constraint satisfaction for any uncertainties and disturbances that have been thought of. As long as you have an outer box on both your measurement uncertainties and the model uncertainties, then we are guaranteed to never violate any of those constraints. This is a computationally simple problem to solve, just a quadratic problem. So the computational time just depends on how long your prediction horizon is. And finally, it's a high degree of autonomy. It's basically you just input a starting point and an end point, and this method will get you from wherever you want to wherever you want, from where you are to wherever you want without any limits. However, this method also has a downside, such as it has a linear performance in a nonlinear environment due to the fact that we are forced to use a linear model. Performance is subjected to tuning, and this is since there's an MPC and there's some parameter selection with the LMI and stuff like that. It is not easily understandable how to actually tune this system properly. Finally, it's also very conservative. We are considering outer boxes on the uncertainties. So if the uncertainties are smaller, then they will still you have to consider the worst case scenarios. So it will have a more conservative performance. So finally, we'll do a case study here on Eros where we'll demonstrate the MPC. So the goal is, of course, to circumnavigate the asteroid and then to land or descend onto the surface. And as you can see here, you'll see here first on the left, we start at many different, well, now we start in a box, 5 by 5 by 5 kilometers with each 5 kilometers where the starting point. And the goal is, of course, to descend into the crater in the middle there. So the way we do it, you can see here that it circumnavigates and keeps itself outside this keep out ellipse until it enters this pyramid, which is where we have defined that now you're in the descent phase. And once it's inside the descent phase, we just change the constraints and then it successfully descends all the way. So on the right side here, you can see it's more or less the same results where we have already started inside the descent space and then all trajectories go towards where we want to go. Similarly, we can see that in the input in the thrust that is generated by the spacecraft here. The optimization problem, you can see here by the lower figure on my left here. It is, as you would expect, it has a very distinct acceleration phase, coasting phase, and then braking phase, and then acceleration towards the surface. But when you see on the actual input that is applied, which is the upper figure, you can see how the uncertainties affect the spacecraft thrust and how it compensates for it to be sure that it still is satisfying all of the constraints and it's still following the nominal system as generated by the MPC. Finally, you can also see the fuel evaluation of the spacecraft, where you can see the clear again, this is a clear separate acceleration phase, coasting phase, and then braking phase for entering into the descent space. So finally, I will just talk a little bit about the future work. My first half of the PhD has been dedicated to theoretical analysis and development of new techniques, which is what I've been presenting here now. The second part will now be going towards more experimental part, where I will, among other, where I'm on my way right now. I'm on my way to Naval Postgraduate School in the United States, where we will take these methods that I presented here today and apply them to these robots that you see here and see how they actually work in practice. Forward, I'm also interested in moving away from the asteroids and looking now more at satellite rendezvous scenarios, especially considering that it's a highly interesting topic for both ESA and NASA, or considering both the lunar gateways and other closer to Earth missions where we will have to do much more rendezvous missions in the future. That was it. That was it for me. Thank you for your attention. If there are any questions, you will have to send it to me on mail, and then I hope I will be able to come back to you. Have a nice day and stay safe in the heat waves. Bye.